Well, good evening, everyone. Thank you for joining us tonight for the DSES monthly service Zoom meeting. This afternoon, we have a number of items that we're going to be covering this afternoon. I'm just going to show you the menu, but before we start, I just wanted to see if there's anybody new on the call that we haven't visited before. And I want to welcome everyone. There's let's see who we got here. We got Emil. How are you doing, Emil?
Good. How are you? Thank you.
Excellent. Excellent. Good to see you.
Same here.
And let's see, there's Jim K3 ILC. I don't think we've met, have we?
I used to belong a couple years ago. I paid Myron at our PPRAA club meeting for dues for this month, and I'm testing out this new laptop. I just set it up for Zoom 20 minutes ago, so I'm trying to get everything set up.
Oh, it sounds good. You look good too. So
No,
the laptop's doing great work for you. I need all the help I can get here with mine. So good to see you. And we got Tracy. How are you doing there, Tracy?
Well, I'm doing okay, and so is my co-pilot there.
I can see I can see him.
Yeah, she thinks she's got to be here whenever I'm on the radio.
Okay, very good. Well, it sounds like you got a good team going there. We also have Barry Hansen. Hi, Barry.
Yeah, hi, this is K7BWH in Seattle. I'll hang around for a while, then I'll have to punch out for dinner.
Okay, I won't keep you from that. And I've got Martha Hannah. And good evening to Martha. I don't know whether you've got microphone capability there. I don't see anything else on there. Let's see, am I missing anyone else on here that's new? I see Michelle's on there. We've seen you before. There's Bob Haggart. How you doing, Bob? Good to meet you. Yesterday or day before yesterday. I think that's you. Yeah, that's you, Bob Haggart. And Zero CTV.
This Kafka guy asks himself, should I now show them I learned nothing from facing trial for a year? Liam.
Who is Joseph K?
Yes.
Quotable fictional character 600.
Sounds like you're watching TV. All right, I'm gonna mute you there. Okay, and we got Derek. I see Derek. Hi. Who else we got on here? We got Matt Mathis, KD0EZS. I don't know if I met you, Matt. I don't recognize your calls, but you know, that's not unusual for me because my brain is not as good as it used to be. And I think there's W1XR, Jim Welch. Good evening tonight.
Good evening.
And I think most of everyone else I've seen before here. So, and we got Michelle. Did I say that before? W5NYV. Very good. All right, I think that's about it. Let me share the menu. Let me share the. Let me see if I can make this thing work here.
Agenda. I'll finish the sentence for you, Paul.
I appreciate you doing that for me because I need all the help I can get here. Let's see. Okay, here we go. And screen number 2. All right, so this is the agenda tonight. I don't know if I didn't see Doug Lieber on there. Doug, are you in the are you on the call? I guess not yet. Anyway, he had something to talk about there. We have a STEM homeschool group visit on May the 5th to Haswell, and that's a group from Las Animas. And tonight we've also got a presentation by Lewis Putnam on Ethernet throughput rates for new SDRs. And Glenn is going to talk about the Haswell site dish visit that he had I guess that was last week. And then Bill, maybe you can talk a little bit about the Santa Fe Trail Days. You made a great presentation there to everybody. And I wasn't sure, Roger, whether we'd have time to go through all the stuff you have, because you've got a lot of stuff you're talking about. We may want to hold that for the engineering meeting. What do you think?
Oh, that's fine.
All righty. All right, well, without any further ado, let's move on. And Louis, are you ready to make your presentation today?
Yeah, Glenn was gonna turn the slides for me.
Okay, that's fair enough. Let me unshare and allow him to move right in there. There we go.
Can
everybody see it?
Yep.
Can you see it, Louis?
Yeah,
Okay.
you can go to the agenda or this first slide. Let me see. I think lately there's been a group looking at putting an SDR in the tower, or actually on the feed hub. I think hopefully that's the right terminology. And I haven't been involved in that effort, but I have been working on a thing we call the System 1 receiver. And there's some experiences I've had from that that should be able to provide some useful information to that effort to analyze and field an SDR. So just initially, I'll just cover real briefly the System 1 receiver effort I've been working on, and hopefully show how it relates to this effort. And then talk a slide on just I think one of the main issues associated with putting an SDR in the feed hub, and that is really the link throughput. And so the bulk of the presentation will be analyzing that link throughput. And then at the end, there'll be discussion of, in terms of science experiments and all that we do decide or want to do, what that implies for requirements for data rates. I think one of the things with the SDR that I don't have knowledge of is what, from the ham side, what they plan to use it for. So I really won't be covering that aspect of it, but I think others are much more knowledgeable in that area, and they can probably handle that aspect. And then the very last slide is just some considerations for the configuration. So, go to the next slide. Let me see, this just kind of summarizes at the top kind of things we've done to date or planning to do. With have a total power radiometer. It's uncalibrated right now. We use it primarily to detect strong radio objects when we're doing our mount pointing calibration, and it also can be used with scanning, putting the mount in skies type scans, acquire radiometer data, and use that to generate an image, a radio image of the sky. Let me see, I have a prototype of a pulsar data collection, and it was primarily based on work that Dan has done. And I just basically tried to put a kind of a user interface on front of it to make it a little less kind of batch oriented, more user interactive. And the next item is to get a hydrogen line capability going, and plan to use the Virgo software. And again, just try to put a little bit of a user interface on the front of it to make it a little easier to use, a little more turnkey. The overall goal of the receiver is to kind of have a turnkey receiver at the site that can be used for some basic science type things, hydrogen line, maser, pulsar data collection. In addition to supporting Malco. The receiver currently has an RSP1A for SDR, and its max bandwidth really is around 8 megahertz. And for pulsars, we really need quite a bit higher bandwidths to see dimmer objects. And although we've detected basically the brightest object in the northern hemisphere, but we've not done a lot of testing beyond that. And so I had begun doing a survey of SDRs around that have higher bandwidth that weren't real expensive. And I came across an SDR called ANT SDR E200. And it's a SDR that's similar to the Adalm Pluto SDR. And it's also very similar to the SDR I've seen mentioned for hosting in the hub. So information on that SDR could be useful. The big difference between it and Adalm Pluto is it has a GigE interface for transferring data from the SDR to a host computer, whereas Adalm Pluto has a USB 2 interface. And the Pluto can only achieve around about 6 megasamples a second reliably, which is well below where we would like to be. The E200 also has faster core processing, and it has more FPGA resources, and I'll mention one possibility of using that later on. But,
on the ice, it was thick enough that they could walk on it, and they walked away. And the van.
Pardon?
I think that was Joe. Joe Dempster, can you mute your line?
Hot mic.
That was you, hopefully. Yeah.
Wasn't me.
Well, feel free to ask questions. Certainly, the main point of this is to pass along information that I've acquired. And so I've acquired this SDR. One thing to note about it is it supports a Pluto interface, and it also supports the USRP UHD driver interface. And it's the second one that I'm most interested in because it runs at a good deal higher data rates. You see, I've integrated the E200 with a standalone test GNU radio flow to really try to pinpoint what kind of bandwidth we can get out of this. And I've done some functional testing also. So my next step really is to integrate it into the current System 1 receiver, and I'm just beginning that. But I think there's interest. The information I've gotten on the link bandwidth will be useful since this SDR is similar to the one that's being considered. So next slide, Bill. So I'm not really familiar with the project to do this hosting, but I've just kind of seen a little email traffic on it. So, but one of the critical issues is how much RF signal sample data can we get across the link from the tower area down to the building? and in using relatively inexpensive SDRs. There are clearly some extremely expensive SDRs, so far exceed what we need, but their cost far exceeds our budget also. But so in the realm of inexpensive SDRs, there's basically the data transfer interfaces available are USB 2.0, USB 3, GigE, Ethernet. There are a couple of small cards that are actually PCIe cards, but I'm not considering PCIe, but trying to run it over that long of a distance would be perhaps possible, but not easy and probably expensive. So the table below kind of summarize some key parameters with each of these interface types. For USB 2.0, that's what the SDR play runs at, and so I have direct experience of that. And then there's the AirSpy, the RTL, Adult Pluto, all use the 2.0 interface. They all, the max bandwidth you get out of there is about 10 megahertz, and that's really, it's restricted by USB 2.0. I've looked at the data rates coming in the SDR play and across USB 2. It's probably in the low 30s, and it's that's at 8 megasamples per second. It can run at 10, but I've found it to be subject to a bit of dropout at that rate. And USB 2, just native copper cable can run around 15 feet or so, 5 meters. The main problem is just inadequate throughput. USB 3 super speed, the USRPS SDRs that use that, Nuand has one, and there are others. USB 3 can transfer in the range of 400 to 500. Actually, I think that should be megabytes, not bytes per second. That wouldn't be real impressive. And again, its length is around 5 meters. This is, has more than adequate performance to do, I think, at least a single channel at 50 megahertz bandwidth or so, or more probably. And you can run it the distance if you have these extenders. I haven't done much research into that, but I'm pretty sure you can do that. So then the GigE interface, speed-wise, it sits between USB 2 and USB 3. And the SDR that's in our that I'm working with now supports that. There are some USRP SDRs that support it. And there are some of the Chinese clone types that support that. So the payload data rate is in the range of 100 to 110 to 120, and I'll give more specific numbers here shortly, but just GigE copper can run, I believe, 100 meters, and probably you can go a bit longer on fiber than that, but 100 meters certainly is adequate by itself. Probably the issue is that GigE has pretty high throughput, but it probably won't handle the highest data rates, in the 45 to 50 megahertz at full sample resolution, and I'll talk about that in a while here. So the rest of the presentation, I'm not going to deal with USB type interface, just with the GigE and try to characterize it. So next slide, please. first I want to characterize the GigE link data throughput. Just basically what any application could get across it, and then the next slide will address, the specific protocol involved in transferring data, complex sample data across it. So just looking at GigE, it uses 4 twisted pairs on a Cat5 or better cable. The clock signaling frequency is 125 megahertz, and it transfers 8 bits per cycle across the 4 twisted wires. That's 2 bits per twisted pair times 4 twisted pairs. So the absolute max rate that it can support is 125 megahertz times 8 bits, which is equal to a gigabit, that's the name, and which is 125 megabytes per second. One note is the link is full duplex. You can apparently, there's some magic, transfer 125 megabytes a second, both up in both directions simultaneously on the same 4 twisted pairs. And I'm not sure how they do that, but that's the way the standard is set up. So for instance, in the case of, if you're trying to do two-way radio, whatever you're putting up, the uplink is not going to impact what's coming down on the ray coming down on the downlink. So that's a max raw over-the-wire rate, but it takes multiple protocols to transfer this data from the SDR to the host computer that's processing the data, receiving and processing data. And I'm looking at specifically the UHD driver, and the protocols that are involved are it transfers data across the user datagram type, higher level protocol, which is then layered on the IP or internet protocol, which again is layered on top of the Ethernet protocol, which handles the lowest level Ethernet transmission. And so if you look at those protocols, need to add data onto the link to control the flow of communications. And this little diagram shows what each one of the protocols adds. So Ethernet adds about 38 bytes. That's the header, the frame control sequence or sync. A preamble, frame gap, and then IP, which, well, in general, the Ethernet then has a 1500 byte payload packet, and within this payload packet's where all the application data goes, and within that, IP uses about 20 bytes, and UDP uses about 8 bytes. So the net result is the payload is left with 1472 bytes out of 1538. So I'll just coin this term payload data efficiency. So about 95.7% of the over-the-wire bandwidth can be actual payload data, and then the rest of it is protocol overhead. And so that gives, if you look at 97.5% of 125 megabytes a second, that's 119.6 megabytes a second that's available for application use. And that's the absolute max that you're going to be able to push through there. And that doesn't mean you can actually achieve it, and that's why later on I'll show some measurements. Got pretty close, but it didn't quite get there. There is a way you can slightly increase the payload data rate by running with larger Ethernet frames, and I think this typically people use 9,000 bytes. But what that does is just up your payload data efficiency from around 95.7 to maybe 98% or so. And with that, you can go from 119 to about 122. So it's not a big jump, but it's a little bit. If you were close, that might be useful. The main issue with it is not all network equipment supports it. I'm not sure if the ANT SDR E200 supports jumper rates. I've not done any testing to date to see. And so let's see, next frame then. Clint?
I think I moved it.
Oh, yeah, now we got it. So in terms of application, here we want to talk about actual RF sample throughput. And to look at that, we have this 119.6 max rate. We need to see how much of that we can use for actual RF samples. And of course, that depends on the format of the data that's sent across the link between the SDR and the host computer. In this case, we're using the UHD driver, which is really a driver that was developed for the USRP SDRs. It's relative, I mean, it's open source, so it's not really proprietary, and a number of SDRs can support that beyond just USRP. And in particular, this the ANT SDR E200 can support it. So what we see in the sample messages, that there's 8 bytes of header, and then there's an optional time stamp, which is another 8 bytes. And even though it's optional, I've included in this analysis because I think that in general we would use timestamping anyway. So what that says is that leaves 456 bytes out of 472 to transfer complex sample data. And complex sample data consist of pairs of in-phase and quadrature values. And so that 456 will store as, it'll be filled up with as many of those values you can get. The I and Q values size can be selected, and the options available in the driver are 8-bit, 12-bit, or 16-bit signed integers. And so obviously if we're using smaller 8-bit ones, we can get more sample throughput. They're lower resolution, and then the other end we can get lower throughput but at higher resolution for the 16-bit. But the ANT SDR uses an 8093, actually the one I have uses a 63 chip. Let me see, they also sell a model that uses the 61. Primary difference is the 9361 has higher bandwidth and a wider frequency range. but it has a digitizer that actually digitizes the data at 12 bits. So when you output at 8 bits, the 12-bit data has to be truncated and you lose some resolution. If you output it at select 16 bits, then the 12-bit data needs to be padded to 16 bits, so you don't actually get a true 16-bit resolution. You just get 12 bits inserted into 16. The current SDR E200 does not support the 12-bit option. That's based on my testing, but, which to me is kind of strange. But so using the max sample rate of 119.6, then we multiply that by the packing efficiency in the UHD buffer, and which is let's see, 1456 over 1472. You end up with 118.3 megabytes per second. And if you, for 8-bit data, basically that's 2 bytes for complex sample. You just divide that number by 2 and you get 59, roughly 59 megasamples a second, which is basically 59 megahertz of bandwidth if your receiver will handle that. And then for 16-bit data, you take that 118 and divide it by 4 and you get about 29.5 megasamples per second, which is 29 megahertz. And so we'll talk about here in a few slides what would be desirable in these areas to do science projects. So that's the kind of rates, and these are, I'll say, theoretical. They're just derived them from using math and the formats of various protocols. So decided to do some tests to see what we could actually achieve. So next slide, Glenn. So it did a test. The top diagram shows the kind of the hardware configuration, and then the bullet shows specific versions and such. Basically, on the SDR, we have the UHD firmware loaded, and the way the E200 works, it has an SD card where you can load firmware on, insert it in the SDR, and then boot it up. And you need, for instance, you need a different set of firmware to run the Pluto interface versus the UHD interface. So that is kind of an operational thing that needs to be probably considered if it turns out the SDR needs to run different sets of firmware for different types of operations, then that would mean changing out the SD card in it. But at any rate, it transfers in this configuration of just a single SDR, kind of a nondescript 5-port GigE switch, and then my home computer, which is a Lenovo ThinkStation, and it's connected by a single Ethernet cable to the switch, and there's nothing else on the switch. And so it basically acts as a dedicated link from the SDR to the ThinkStation, and there's no other devices that are on it that are causing any interference or loading. And there's only a single process in the ThinkStation using the link to. So basically, this is, a situation where you hope you can achieve the maximum. Next slide, please. Well, wait a minute. Can you go back? We'll talk a little bit about on the Think Station, the software running. The test runs under GNU Radio, and typically I think most of the science applications we've been running have been GNU Radio flows. Basically, the flow is the UHD driver, which handles the interface to the SDR, and that passes data to a source block, which in GNU radio terms is a block that acquires data from an SDR and then can output it to the rest of the flow. And then I have one other GNU radio block, the frequency sync, which does an FFT and this basically displays spectral data. In a nominal application, it would be instead of just a frequency sync, would be a number of different processing blocks processing the data. So this is just a simple case. I have the sync in basically so I can look at the data and see if I'm actually getting real usable data. For instance, I ran one of the tests with the frequency set to the FM commercial band and see if I can see the kind of the standard frequency spectrum that you would expect with the FM band. And it did successfully do that. Next slide now. So here's just one slide on the results of the test. First, the first set of bullets just describes how I conducted it. There's a parameter on the UHD source block where I'm set wire format, which sets the sample bit width either 8 or 16 bits. There's a sample rate block. I didn't show it, but there's a frequency parameter. And I tried various frequencies from 100 megahertz up to all the way up to Wi-Fi frequencies of 2.4 gigahertz. That doesn't really affect the results at all. And the way I measured the throughput across the Ethernet, I used the Ubuntu system monitor tool. And initially I set the 16-bit, sample size to 16 bits, started with 20 mega sample rate. I was, I knew that would work. And then I incremented the sample rate up till the point where it failed, and then I kind of backtracked in small steps till I found a rate that passed. So, and then when I found a rate that passed, I just changed the bit size to 8 and doubled the sample rate and reran it. And that basically worked also because it's basically the same amount of data passing across the interface. So this table shows, summarizes that result. So, and I didn't show every rate I tested, I just showed some of the major ones. So at 30 megasamples a second, it failed with the 16-bit data. And the actual application rate for that would be 120 megabytes. And then with the full loaded up for protocols, that'd be 126.8, which exceeds the 125 megabytes per second. And so it should fail. If it hadn't failed, then.
Hey, Lewis, how exactly did you notice a failure? Were you getting dropouts in GNU Radio or something else?
No, I was a little surprised that I thought what would happen is I would just get dropouts, but what happened is it started up and I got a message, in the sysout from the driver, and then it didn't do anything. It didn't So it did not do what I expected. And that's why I say it failed and not data dropout. And so I'm not sure if it can detect, you know, that you're asking for too much data and give a different error or not, but that's what happened.
Hey, Lewis.
So I'm back, pardon?
Hey, Lewis. How
Yeah.
long was your test cases? How long did they run?
You know, I let some run for 20 minutes. So there was, you know, one note I will say, there's a default buffer size for the Ethernet, or for, excuse me, the UDP data. And the default value in the system is too low. And you have to, there's some Linux commands you have to run to increase that. The good thing is that the driver will tell you that it's too low and tell you what commands to execute. So it's when I executed those, did not execute those, the max data rate, I'd see dropout probably in the 20 to 25 megabyte or 100, excuse me, 20 to 25 mega sample rates. I'd see occasional dropouts, and anything higher than that, it'd be very frequent. So, but when I changed, up the buffer size, then I didn't see data dropouts. Like I said, I ran some cases at least 20 minutes. So I think that's well past the point where it would be slowly getting behind. So at 29.5 samples per second, the estimated megabytes per second is 124 points, or excuse, 124.6. One of the things I should point out, the tool outputs the Ethernet rate in MB which is that's really the power of 2 megabytes, not the decimal megabytes. And so I had to convert that to just straight megabytes per second so I could compare it against my estimated rate. And so I estimated 124.6 and it said 123. Now that doesn't entirely make sense. It should be at least 124.6. Did a little research on the Linux tools that will give you Ethernet data rates. And what it said is that they tend to be somewhat low because they don't account for all of the Ethernet protocol. So that's consistent with what I see. So let me see. Then I bumped it just 1/10 of a megasample per second up 29.6 and it failed. So it's somewhere between those two values that. And if you look at the estimated megabytes per second for 29.6, it's 125.1, so it exceeds the link rate. So what this really shows is that actually you can get much closer to the max link rate than I thought you could actually achieve. I'm guessing that the USRP folks have really fine-tuned the UHD driver to make it run really well. But then I, did the test where I have the sample size from 16 to 8 bits and reran it, but I doubled the data rate to compensate. And so it ran at 59 megasamples per second, and the data statistics across the wire just looked exactly the same. One thing I note, the tool was updating the rate about once per second, and it was extremely consistent. It just basically didn't vary except at the very front end when it was starting out. So I think it's probably a valid test, but it's also, you know, truly is a max achievable rate, I'm sure. And if you've got other stuff going on and all, then you know, that link potentially is going to be shared by other users. So really need to leave some margin. So next slide. So that tells us, you know, the maximum sample rates we can hit around 59 megasamples for 8-bit data, which is 59 megahertz, and 29 megahertz bandwidth for full resolution samples. But what do we need to run some of these science operations? Well, there are two main things they're doing is the hydrogen line stuff and then the pulsar stuff. The hydrogen line is and also masers is done very similarly, or done at 1420 for the hydrogen line, and then the masers are in the 1600 to 1700 megahertz range. But you don't need a lot of bandwidth. These are like spectral lines. The reason why you need bandwidth is because they get Doppler shifted, and so to cover the Doppler shifts that you see, you know, in the Milky Way, you need somewhere in the 2 to 3 megahertz range, more or less. Do have some hope of doing some hydrogen line on other galaxies, and I think their Doppler rates are a little higher. I'm not quite sure what they would be, but if you look at the data rate you need for a hydrogen line, you just need around 3 megasamples per second, 3 megahertz bandwidth. So that's well within the capability, and it's well within the capability of USB 2 based devices even. Pulsars are a little different story. Basically, the higher the bandwidth that you have, the dimmer you can go on the pulsars, except potentially for RF5, which can cause issues. And so, kind of ideally, we'd kind of like to run in the 40 to 50 megahertz range, and professional installations run it, you know, upwards of gigahertz and stuff, but that's out of our range. So if you look at that for 50 megahertz, say, that's 50 megasamples per second, and that would take 200 megabytes a second, which exceeds the length. If you use 2 bytes per sample, then that would take I'm sure I did the math right there. That should be 100 megabytes per second. I don't know where I got 50 on that. That should be 100 megabytes per second, which is within the link rates. So there are some things that could be done to reduce the bandwidth. One of the first things that's done with the data in the signal processing computer is to perform an FFT to convert it into spectral data and then average that down. And so if you did the FFT and the SDR in the averaging, you could cut the rates by quite a bit. Basically, for pulsars, you need a spectral sample rate of, you know, anywhere from 1 to maybe on the high end 10 kilohertz of spectral samples. And for each spectral sample, we're typically using 1K FFTs, so it's 1024 frequency bands, and then it's typically floating point data. So that'd be 4 bytes per. And if you do the numbers, that spectral data would take 41 megabytes a second. So that's, a good deal lower. And I think the SDR that I'm looking at has enough FPGA resources to do the FP, but it's a good deal more technically complex than just doing basic software. Then with spectral data, you can still compute total power radiometer data by basically kind of adding up each spectral band. It's a little more complicated than that, but not much. So that would support both pulsars and total power radiometers. One of the things I'll say, these data rates are for a single channel. I think there's some desire to do, dual polarization for pulsars. And so basically you need to double these rates for dual polarization because you're getting 2 streams. And so while a single channel is definitely feasible for 8-bit data on the pulsars, 16-bit, you have to go to a lower thing, and then you're going to do channel, you got to divide those numbers by 2. So that's what I think can be done with that link, with the kind of science data that we're looking for.
And just to comment on the output data rates is, I guess I'd have to do some comparisons, but I would probably prefer to preserve the 4-byte resolution and drop my bandwidth down to 25 megahertz. So I'd use lower bandwidth, but keep the higher resolution.
Yeah, you would have the flexibility to select that. I mean, it's not a parameters that you have to set, during design time. One of the things I've seen is that, what surprised me, I've seen some of these bigger astronomy sites, they run with very, 3 and 4 bit sampling rates and such. So, of course, they're running a lot higher data rates, but obviously when the resolution, you just lose, the lower level signals, but there's also a lot of averaging going on in pulsars. So I really don't know. Certainly you can detect pulsars with 8 bits because they've done it with the RTL, SDRs and such, but they're not the, certainly not the dimmer ones.
So all of your analysis was on copper. Is it the same results if you're on fiber?
I think the clocking rates and all of that are the same for fiber. I don't think it's not higher rate or whatever. That's fine. I haven't really researched it very much, but that's what I think it is.
Okay, yeah, I was just wondering if there's 10 gig fiber adapters.
Oh, yeah, and if we go to the next slide, I'll these are just some things I think for you guys to think about. One of the ways that you can maintain, do dual polarization without taking as much of a bandwidth hit. Basically, the SDRs have 2 channels, but when you run those 2 channels through there, they're sharing that one GigE link. So it's the GigE link that's limiting here. But if you went to 2 SDRs, you could they each would have its own GigE link. And so you could run each one of those channels at a higher sampling length. The other thing is it just gives you some redundancy out in there in case one of them failed, you could go to the other SDR. If you did put 2 SDRs in there, you need a higher data rate link from the tower to the building. Yeah, I think that's what you're alluding to. And so that's the second bullet. That Ethernet switch in the hub would need higher uplink between it and the building. And I think there's several ways you might be able to put multiple GigE links. You might be able to go to single or multiple 2.5 GigE links, or go to 10 GigE. And the switches to do those things aren't terribly expensive. I'm not sure about if you're routing it on fiber, what the adapters and all run. I think it would be a good idea to do that. Just one, to have margin, so you're not right on the ragged edge. And then so you have some growth to maybe if some of the SDRs will come in at higher bandwidth downstream. And rather than having to upgrade the whole thing, you would already have the higher bandwidth in place. Now to use that higher bandwidth, it's you would need to update the signal processing computer in the ops building also to get a higher link rate into it. And so it's the same basic kind of options that you'd use for the uplink to the hub. Multiple links or GigE or 10 GigE. One of the things I did a quick look at, and I don't see any SDRs that are in the lower affordable range that have anything beyond GigE. You can certainly find higher ones in the more expensive equipment. There's some that I think have 10 GigE actually. So that's a possibility if you got the money to do it. So that's kind of covers what I've discovered. And I'm open to any questions.
Hey, Louis, I have a question, and it has to do with more about the CPU utilization versus the network card. 10 or 15 years ago, a lot of the issues I had was I was overwhelming the CPU when I was trying to drive the Ethernet card faster. So I don't know if you've seen any of the CPU utilizations right now. Since it's been so long ago, maybe it doesn't make any difference. But at the time, I was really pounding the CPU, talking to the network card as much as the network traffic itself.
Yeah, I think the technology now, I know the SDR has it. They have call them offload data engines, and so if they do, that basically CPU appears to basically just set up a DMA, and then all the Ethernet overhead is handled by that dedicated hardware. And what I saw, I mean, I can't see the loading in SDR, but for the workstation I have, I ran kind of a full up pulsar processing chain where it does FFTs and averaging, converting it to power. And only thing I didn't do was data storage. And I ran it at 59 megahertz and with the lower 8-bit data. And I ran like 8K FFTs instead of the lower 1K ones. And I still, with the machine I have, I didn't get over probably around 30% usage.
So maybe it's a non-issue these days.
I think that the systems are, I think a lot of that stuff has just been offloaded and,
Sometimes it depends, at least at the time, which type of driver you had with the version of Linux you were running that would cause issues, but that's probably maybe gone away too.
yeah, I mean, I was remembering back that same time, and so I was expecting the max achievable rates to not exceed 100 megabytes per second at best. And with this thing, again, it's a fully dedicated link with nothing else going on. So, well, I would say there is a little bit of command and status traffic between the driver and the SDR, but it's apparently very small. You can't see it in the numbers. So
Okay. Yeah, I wasn't quite sure what you were seeing as far as the CPU. So,
and I mean, that's a point for the system one receiver. I have this pretty low powered processor in there, and so I'm pretty sure it won't handle 50 megahertz without, probably won't, but I'm pretty sure the computer that they have out at the site now that Dan has been using, I think it's got the power to do it.
This was very helpful, Louis. I really appreciate the analysis because even though you're using a slightly different SDR than what we're thinking about, your analysis is on the GigE link itself, which doesn't matter which SDR. So, this is one reason why this would work great for hydrogen and masers. For pulsars, this is one reason why we're preserving the ability to switch. So if we do put an SDR up in the hub, then the user can switch. The user can choose either INQ data down on fiber, or we'll still have RF on the coax available, just like we do now. So that may be what we do if we're doing wideband pulsars, is just use the RF on the coax.
Right, yeah. The main thing, this is very doable, but we're trying to do it at a lower cost, and then that just puts additional constraints. So,
this is Roger. I'm kind of having a side conversation here. One of the things I'd like to see is for us, before we start looking at putting stuff in the hub, is just to run a test. Put a B210 in the hub, see how good the data is we get from it, and then run a B210 down in the building and see if the data is just as good or if it's degraded. If it's degraded, certainly putting the SDR in the hub is the way to go. But if it's just as good in the building, we have a lot more flexibility if we can work at that end of the coax rather than putting things in the hub.
Oh, hey, Roger, we can't do that test because the B210 runs USB 3.
Okay, then pick another SDR that we can do an apples to apples comparison.
Sure, one of the newer ones we could.
Yeah.
Yeah, I mean, my E200 could be used for that. You couldn't, run it at the high, as I've said, you can't run it at the 16 bit sample at the highest megahertz, but you probably wouldn't need to do that just to see about signal quality.
Yeah, and that's what I'm interested in is the signal quality. So since we do have the preamp up there in the hub, does it lift the signal enough that it doesn't matter if we put the SDR in the hub or down in the building? And before we start heaping a lot of complexity into the hub, I'd like to get that answer first, because if it's exactly the same, it's certainly better for us to run that equipment down in the building.
Yeah.
I'd like to follow up with with, I'm going to vie for the stupid question of the evening here.
Yeah.
I was, up until the beginning of your presentation, I was under the impression that system one was the positioning system for the dish. Could you give me a definition of what system one is, since it's obviously much more than just the positioning system?
I think most people think of it as the positioning system, but initially we needed a way to calibrate the mount, and we wanted to calibrate it, the mount pointing. We wanted to calibrate it by looking at known objects on the sky rather than doing some kind of terrestrial thing. And so that's when put together a receiver that would do just total power radiometer. And we used it for that. I always kind of had the idea of expanding it beyond that. So that was the first capability, and that's what's resident on the site version out there. It's in the rack, kind of behind the system one monitor there. It's in that rack. So I don't think anybody's used it outside of us. It was my intent to, get a user's manual and all that stuff, and maybe some training to help people use it, because, the hope was that it could be used by people who are only just interested in going out and doing science, and weren't, radio experts or didn't want to bring equipment out to support that, and also potentially for students to use. So that was the idea behind it. The pulsar stuff prototype has not been installed on that computer or the receiver yet. The receiver just basically consists of an SDR, which is the SDR Play. And then it has a processing computer. It's an NVIDIA Jetson Nano. And so it's like 4 ARM cores at fairly low rates. So it can do the pulsar processing at 8 megahertz. I would guess that it could go up to maybe 15 to 20 megahertz. But what it does have, and what I was hoping to use to increase that, is it has kind of a GPU in it, and use the GPU to kind of increase the FFT throughput rate and get closer to 40 megahertz. But that again is a technically complex thing, takes time. I will say I'd hope to have it up and able to hand off, but I've gotten sidetracked with the encoder upgrades and then these new tracking algorithms. So I've been kind of sidelined on the receiver for at least a year or so.
Louis, I understand that can also do the raster scan and keep track of coordinates to altitude as well, right?
Right. The way the calibration works is it does a cross scan. It does a horizontal, a scan in azimuth, and then a scan in vertically in elevation, taking radiometer measurements along that scan. And that's used for the calibration. We also have the capability to do, I'll just say, call them rectangular scans. And you can take radiometer measurements at each of the scan positions, and then you can take that data and convert it into RF images, if you will, of the sky. Now they're low resolution because of the beam width is like close to a degree, so that's the kind of resolution you get is like 1 degree on the sky. But I
Still image some of the, like, we could image like Cas A or whatever, some of the nebula and stuff with that capability, right?
pardon me.
We could do imaging with that, couldn't we?
Yeah, and you know, as a part of doing the Mount Cal, it was kind of impossible just to look at the data and make sense of it. So I developed the capability to display it, and so that you could see where the brightest points were in relative to the bore side.
Yep.
And I'm pretty sure, you can correct me if I'm wrong, Glenn, that display capability, I think we have that in the laptop now.
That's correct. Yeah, that's in the system one side. So the other thing that Roger may be interested is there's a single TCP/IP interface between the System 1 console to the NVIDIA. And so that data, command and data is passed across that single line.
Right. We've implemented, an interface so that the System 1 mount controller can turn the, control the System 1 receiver to turn it on and off and take data, at the scan points. And so there's a protocol for that. I don't think for pulsars we probably need to do that, because basically you point at one location and then stare at it for hours. So there's not a real need to automate that. Now, what I will say is for hydrogen line, I would hope to be able to do scans when doing the hydrogen line, and then that would provide data for the generating images of the Milky Way and doing that type of analysis. So, and you wouldn't have to do so much manual work. You could just do a set of scans and, along the galactic plane or whatever, and get that data. And that data is logged as, actually it's CSV data. So you can, almost any, whatever software you bring to the table, as long as it handles a CSV, you can, handle that.
And obviously, our SDR doesn't preclude the use of the other SDRs. I mean, that's only something that we control for what we're doing currently.
Did that clarify it at all, Roger?
Yeah. Thanks.
Hi, I have a question regarding observations, pulsar observations, and this is I'm not sure if it's even relevant, but in regards to pulsar observations, specifically with maybe perhaps millisecond pulsars, and looking at the signal at these wider bandwidths. Would the signal dispersion have any kind of impact on the received signal in terms of how that would be analyzed, or is that even relevant? Does anyone have any idea about that?
I think, the data that we're logging for pulsars is spectral data. And the reason, total power data would be adequate to detect pulsars, except that the arrival time of the pulse is affected by the scatter in, the intergalactic medium, not that, or interstellar. So what you have to do is kind of line up for each spectral band, line up when the pulse gets to that band, and line those all up and then sum it. And so that's why you need spectral data. And that lining up process is done post data collection. Tends to be a pretty intensive math process. Dan probably knows a little more about it than I do, so.
No, you're exactly right, Louis. That's how it happens. It's post-processed in Presto. I'll just make the comment. The reason we can de-disperse the data is because we're looking at known pulsars. So we know the distance, we know the dispersion measure, so we can de-disperse them since it's a known pulsar.
And not only we know the dispersion, we know where to look. So we're not just looking, we're not doing searches for unknowns, so we're just happy to find knowns at this point.
I see. Great. That answers my question. I appreciate the response. Thank you.
Thank you very much for that presentation, Louis. It's awe-inspiring. There's so much for us to learn. That's for sure. All right. I'd like to see if I could get Doug. I see Doug Lieber's on the call, and he did have we have a STEM homeschool group coming out on May the 5th, and I'd like to have him just kind of let you know what we're doing and what he needs in terms of maybe some volunteers and resources. Are you okay there, Doug?
Yeah, can you hear me okay?
Perfect.
Great. So we have contacts with a homeschool group in near Los Animas that currently is about 25 children aging in range from 9 to 14, with a median around 10 years old. They don't have any particular background in science or astronomy or radio, so they are fresh. And what the group would like to do is develop a relationship with us so that we could have some workshops over the coming year to teach them about astronomy, radio, whatever we'd like to do. So it's pretty wide open. So they don't know much now, but there's a potential that we'll have a few good students there that are nearby and interested and willing. So on Monday, what we can do depends a lot, on how many folks are able to come. Right now, Paul and I will be there. And I've just said that we would do a tour of the facility, do a demonstration of the ham radio equipment, and show them what, some of the things that are, or talk about some of the things that we can do. I'd really like to have some hands-on demonstrations that would be, that the kids could participate and learn from. And so I've got, several, simple ideas of making small antennas and looking at signal strength and maybe doing some radio direction finding, but it's wide open. And we might do things like teach them how to use a multimeter. What we don't have right now is something related to astronomy. It would be wonderful if we had access to a little bitty telescope, show them something that they're going to see the big dish. It would be nice for them to see, oh, maybe this is something we could build at home. So I'd like to find out if there are any members who'd be available on May 5th who would like to do a demonstration or would like to participate in helping kids learn about electronics, radio, astronomy. So, what we can do will just depend on who's able to join us.
Are there any volunteers? Hands up.
Yeah, I apologize, Paul. As I told you, May is kind of toast for me. June, I'll be available again.
Understood.
What day is May 5th? Is it?
It's
Yeah,
It's a Monday.
it's a Monday.
A week from today.
Yeah, they can be on site for up to 3 or 4 hours. We're thinking midday, starting at 10 or 11.
And they bring their own lunch and everything else, so they're pretty self-sufficient.
And they'll have the kids will have their at least one parent with them. It's a well-controlled, good group of folks. And next year, the group is probably going to double in size. They're going to make connections with La Junta, and they may have as many as 60 kids. Again, the age range will be pretty wide, and I don't know how many, 10 to 12 to 14-year-olds would be the ideal range that I'd like to work with. But I think the kids will be fun. I'm looking forward to it.
Okay, well, thank you very much, Doug, for putting that out there. And we'll maybe you can maybe put a note onto the group IO and see if we can have some other folks just to kind of help us control the groups and make it through there. I've got a video that I can show on the big screen there of I bought some of these how the universe works series, and I got them on my laptop, so we can project that on there without any problem. All right. Let's see. What else? So Glenn, you had a visit to the Haswell site last week?
That's correct. Lewis and I went down there last week. Our main mission on that trip was to do our first integration of the new mount control algorithms. So we've been working on these new mount control algorithms and software since probably late last year. We've gotten it to a point where we could actually run it, and we wanted to see if there was any variation between how it ran with our simulators and how it ran with the actual mount. We got down to the site, and we came across 2 or 3 things that caused us issues. There were really 2 main issues that occurred while we were down there, and it had to do with the control of the azimuth axes and the elevation axes. When we were running it, something that maybe I should mention real quick is the way we're doing our testing is we created this standalone Java process that's the mount controller, and then we have this other process which is a GUI interface that's a test controller. And using that GUI interface, we can plot the data that's coming back from the mount, and we can see what's going on as we command it and as we track objects. So after we got everything set up and made sure everything was connecting correctly, then we started running our tests, and we noticed that we had problems in both axes, and the problems were totally different. So the first problem we addressed was the azimuth axis, and we were seeing something very strange there. It was basically tracking along the edge of where the trajectory was at. We normally expect it to go across the trajectory back and forth, but it was basically stuck on one side. After 3 or 4 hours of really pounding our heads, we found a software problem. We were able to make the software problem. We were able to do a quick fix on that, and that basically took care of the azimuth issue. So we feel confident that the way the algorithms are working for tracking on the azimuth axis, everything's working correctly. The elevation axis, we kind of got to around 3:30 or 4 in the afternoon, and we kind of ran out of time, but we did see something odd on the elevation axis that I put it in the memo, and I'd like to maybe discuss real quickly with the folks here. And what we saw on the elevation axis is that when we were going to track the trajectory on the elevation axis, it always overshot that trajectory. So essentially, if you look at the presentation we did maybe last time or in January, there was this box, and in that box, we're trying to stay within that box. And what happens is when we come to that edge of that box in the elevation axis, it would travel beyond it, and then it would come back in. So basically what we were doing is we're having overshoot problems in the elevation axis. And it appeared to be, and Lewis can chime in if you'd like, but it looked like we were about maybe 0.2 of a degree overshoot almost every time. So we tried debugging that for quite a while, and we couldn't seem to make a difference as far as some of the parameters for the algorithm to keep it within that box. So what we did is we transitioned the System 1 software and hardware totally out of the way, and we went to use the manual system. So the manual system has the rheostats and the switches where you can control them out manually and not have any software or hardware in your way. And essentially what we did with that is we just kind of commanded the elevation axis up and down and up and down, and it was doing the exact same thing. So we would turn the switch off, or we'd go from up. There's kind of a three positions. There's up, center, which is off, and down. So we would transition, and when we get to the off or the center position, the mount would still continue to travel about 0.2 of an inch or 0.2 of a degree. So basically, it meant our algorithm wasn't in the way, our hardware was in the way. There's something else going on with the elevation axis that we don't really understand. Now, what I said in the memo I sent out to some folks was there kind of we have some hypotheses, but we really don't know what the answer is. One of them is that maybe the new feed, the weight of the feed itself is somehow changing the characteristics of the elevation axis itself, the extra 80 pounds or whatever it is. Don't know if that's it or not, just an idea. Or something has changed in the mount control electronics where maybe the brake itself is not engaging correctly, or it's engaging slowly. So when we say off, we assume the brake is going to engage and then the elevation axis is going to stop. But that isn't what it appeared to be happening. So once again, we don't know if that's it, but that's a candidate. And then another candidate is that between us and the mount itself, or the elevation axis itself, there's a mount control box. And so when we're actually commanding the axis, it goes through that box, and that box has hardware, software in it, and maybe it's doing some type of ramp down, some kind of automatic ramp down that we're not anticipating. So when we command it off, maybe there's a ramp down algorithm that it initiates, and then it slows down the axis and it stops. So those are the kind of things we were seeing on the elevation axis. We're unsure of what's causing the problem, and it needs to be investigated. If it's a brake issue or a brake engagement issue, then we may have some, we need to be careful about what's going on with the elevation axis.
Yeah.
So that's kind of where we're at.
Then is it the same amount going up or going down?
We didn't get we can't look at it that finely. To me, it looked to be different between the two, going up and going down, but I'm
Yeah.
not sure. What did you think, Lois?
Yeah, I think going up, it didn't overshoot as much, which would indicate some gravity issue.
Yeah. Glenn, can I make a comment?
Sure.
I would say it's either backlash. We're driving this with very large gears.
Right.
So there can be quite a bit of backlash, and it could also be the Allen Bradley controller. It has internal programmability that has this ramp up, ramp down capability in it, and we've never gone in and investigated exactly what that thing's doing.
Yeah, and that's what I meant by that third option, where there was this mount control box that actually did the ramp down. It's that Alan Brady box, like you're saying. And it could very well be that.
Do we have the manual for the Allen Bradley?
No, but it is a standard industrial box that we can probably pull it off the web.
Yeah, because it'll have, yes, it will have one of those slow down things in it.
Yeah, it has quite a bit of
it'll have a built-in ramp.
Yeah, it has quite a bit of programmability that we've never used.
Yep.
Yeah, I actually have the manual, but what an additional comment is the brakes for the elevation used to be really quite loud, and they were not making a lot of sound when you would turn it to an off position, which led me to think, I've kind of wondered if the mount controller does ramp it down, but earlier the brakes would fire and kind of, short circuit that ramp down.
Yeah, maybe
just-
we need to test the brake. That was the first thing we probably ought to do is test the brake.
I agree. Now, the one thing I did notice is you can hear the brakes being retracted. So when we command it to go somewhere, you can hear the sound of it retracting. That's something that we typically hear
On the elevation?
on the elevation. Yeah.
Okay.
You can
I know
hear
you
that. But the other side of it, like Lewis was saying, we thought maybe it used to be louder. So, but if someone knows how to do that brake inspection, I would really recommend doing so.
Well, that's the Allen Bradley and the brake can get into a fight if you're not careful.
That's
Well,
true.
what I will say is the Allen Bradley controls the brake. It basically
Right.
throws a relay that engages the brake. So it has the level of control that it should be coordinated on.
Got it.
Yeah.
Okay.
I have a question.
Yes, sir.
Is it possible to monitor the current that these devices are using? You said it's only elevation, not azimuth, that's causing this. So can you monitor the various controllers that are causing elevation to occur? I mean, you're driving it, it's driving because you can see it, and then it overdrives. So is there a point that you could monitor a current to see, well, we stopped inputting, we're no longer providing a drive input. Now, with respect to timing, is it possible to see that it drops off so many milliseconds after you've removed the drive input, or does the current still the current still engaged? In other words, you can tell if it's gravity or a drive by looking at the timing.
It takes some work, but it can be done.
Okay.
We have current transformers and get up there with a current probe and a scope and watch it. But then you have to be able to drive it while you're up there, so that's tricky.
Well,
to
I was
be in
picturing
the
it being
tower
done
and
down at the control room,
Yeah.
not up there. Not
yeah,
up
all of the current devices, the motor controls are all in the tower.
Oh,
And so you have to monitor the currents in the tower
see.
while you're driving the thing from the console. I
Okay,
guess we
that's
could use
not so convenient.
we could probably use the old manual controller and drive it from the tower itself
Correct.
while we're looking at it. So that's a possibility. But yeah, that's something we should probably do.
Or
Yeah,
you
the
have
thing is-
or you have some guy in the control room with a hand on the button, like me, and a handy talkie.
Yeah,
Well,
but
to
it's
be-
real hard to tell when you stop driving that way.
Right, it's pretty imprecise.
To be quite honest with you, we could take a laptop to the top of the tower and plug it in. We could run it from up there and not have to run it from down in the building if we had to.
Yeah.
But I think, Lewis, have you been looking at some of this stuff before in the past, weren't you? As far as the Allen Brady and driving it?
I've looked at kind of the basic, like Bill said, there's a lot of parameters. and some of them are associated with ramping it down. I don't know what the parameters are set at. I mean,
I think we have it set like as just a basic pulse width modulator controller.
Yeah.
So there aren't a lot of settings that we've added, but the thing can be used as the full control, ramp up, ramp down, speed control, everything.
That's true.
I did want to say we did discover a bug. We put it into commanded it to go to the store position, and it overshot in both axes while we weren't watching it, and it went over the top, went to 85 degrees on the south side, so it went all the way through 90 over to 85 degrees in elevation, and the azimuth went around to like 8 degrees where it should have gone to 314. And so then it took us a while to figure out, well, did we wrap it entirely or did we only go past it on one side? We finally decided, Roger went up in the tower to determine that we weren't completely wrapped. And so we brought it back to 314 and overrode the limit switch that prevented it from going any further than 85 over the top. And so that was a bug that shouldn't have happened. We just Paul commanded it to go to stow, and it didn't do it.
Well, let me talk like the software engineer I am. And, and I'm going to say that's not possible. But obviously it did. So something else is going on. So I don't know if some kind of, did the encoders get dropped? You know, did we lose communication? The encoders? Did we have some kind of hardware issue? You know, was the wind blowing 100 miles an hour and it was pushing them out? You know, I don't.
How heavy is that thing?
It's heavy.
Yeah, I know.
It's not going to stop on a dime, and and 3/10 of a degree is nothing.
I'm not talking 3/10. I'm talking 5 degrees over the top, and I'm talking probably what 20 degrees to the on the azimuth.
Yeah,
More than
Well,
50.
I'm talking about the original problem.
Yeah, the original problem, right?
Yeah.
I guess, like I said, you know, I have never seen the mount do that ever. And I've bounced it all over the place. So something odd must have happened. Now, is it a software bug or hardware bug? I don't know. We're just going to have to track it down.
You can just blame me because I'm the guy who pushed the button.
Didn't you grease everything?
Yes.
you just greased everything and worked over the slickness.
That's the problem. It just slides right over there.
Yeah. But no, but you've just taken care of it. It was used to being dirty. It's not dirty anymore. And that actually may be part of the problem.
It could be.
If it got grease on the brake, that could be part of it too.
Yeah, that would be bad.
So basically what I do every time we bring a new version down to the site is I run through all these tests that include stowing the mount or moving the mount to different places to see if limits get hit. Does the software stop the telescope from going over the top? And I test all those conditions before we ever take a version down to the site. Now, once again, we have simulations of the mount. We don't have the real mount, obviously, here in Colorado Springs. So I try to test all that stuff before I take it down to the site. So that's why I'm saying we got some kind of different combination here that we just need to track down.
Yeah,
the solution on the last issue was, guys, if you stow the dish, don't just assume that the automatic is going to do it perfectly every time. You've got to watch it. In fact, anytime you move the dish dramatically, you should eyeball it and make sure that everything is going the way it should.
I agree completely.
Last time I was there, Roger, at the end of the session, Roger showed me how to stow. So I played with the stow, and I of course I was watching it because did it auto and then I did it manually just to play with it. I went a little bit beyond and came back. So it worked perfectly then. I would say perfectly. It was the only time I'd ever done it, but it behaved in a predictable manner when I saw it last at the EVE.
Yeah, this was a fluke.
Yeah, Bill.
And I do it every time when I'm there. I stow it every time. So I've never seen it. So
we'll test that again next time.
Yeah.
I'll be there on Monday.
Oh, okay.
Maybe if it's not too windy, I can move it around. I'll let you know if I break it.
Okay.
One comment I'd like to make, if we have an an elevation brake problem, it's really those elevation brakes that keep that thing in the stowed position. So I think we just need to put a little priority on looking at the brakes to make sure those are not the issue.
Right.
That motor, the elevation motor is really high RPM. When I looked at it and watching it go, it's very, very fast. So it's got a lot of momentum. So, the brake has to be able to take that energy. I've seen it work, and it seemed to work pretty good.
Yeah, Bill,
no grease on it. I'm sure of that.
Yeah. Bill, I wrote up a problem report, whatever you want to call it, as best I could, because we were lacking a lot of information. So it was full of apologies to Glenn about not having details. But yeah, I did send him what we saw.
Good.
So he was aware of it.
Yep. I just wanted to bring it up here so we didn't lose it, but
Yep.
thank you.
Yeah, I appreciate it. Thank you.
Okay, guys. Well, we've killed 2 hours here, but it was a fun 2 hours, and I think if you maybe Bill, you want to follow up on that issue that we're having, and I'll let you know what I hear or what I see.
Hey, did you want me to give a report on the event?
Maybe we should hold off on that until. Do you want to do that on the next meeting?
Not really.
Okay, then do it.
If the group
flexible, man.
if the group doesn't mind,
Go for it.
because it's fresh. So
Talk fast.
well, all right. Let's see there. Let me get some stuff up here. Hang on a second. All right, I'm gonna share this.
While Bill is doing that, Paul, I actually can't make the engineering meeting because that's the one that always conflicts with the PPRAA board meeting that I have to attend.
Yep.
Who's that guy? Jeez.
Yeah, there's that handsome devil there. Okay, let me talk about this. Before I forget, one thing I wanted to mention was Bob Haggart brought down all of his spare parts from his lab and some radios, some VHF radios, and a TV monitor for our site. I wanted to thank Bob for all of that. He spent a lot of time sorting that stuff out, bringing it down in his van, and participating in this event. So I appreciate it, Bob. If you're still on there, thank you. We'll have to go through and sort all that and get it in usable place in either the bunker or the building. So let me talk about the event. We had Rob McMasters as a member. I don't think he's on tonight, but he's a member that grew up in Los Animas, and he currently lives in Idaho. And he organized an event following the Santa Fe Trails Days that was on last Friday, on the 25th of April. And that was for this event that he organized was for the teachers in the area and interested parties from the surrounding communities. A lot of these people Rob grew up with, so he knows a lot of people down in the San Luis, or not the San Luis, but the Arkansas Valley area. And they have a lot, these are people that are all locals. They have a lot of resources. They know everybody, and they're a really good group to do an outreach with. And so we decided to do this luncheon and tour and demonstration of the site for this group. We had about 10 to 12 or 10 to 15 adults, 8 to 10 kids, and about 8 of the DSE members in support of this event. I didn't get an exact count. I don't know if anybody else did, but that's about right. So we probably had about 30 people down there, probably 35. Rob paid for a catered lunch from the Los Animas Mexican restaurant of Carmen's, and he asked for donations from the people who attended, and he ended up raising us a little over $400 for the DSES group just to host this. So that was great. Rob had also purchased all the chairs that we used in the classroom. So all those black or dark gray chairs that we have, Rob paid for all those. That was about $600 that he donated to us for our classroom down there. So that's nice. So Paul and Bill Thomas manned the DSES control console. There you got a picture of Paul at the console. They were setting up for an EME demonstration. And while they were doing that, we had lunch, and I did a presentation on the history of the dish and the site and the DSES organization, as well as all the things that we do with the dish. A lot of people ask, well, what do you do with this? And so we had a presentation. A lot of it was taken from my SARA presentation that I presented at the Western Conference for SARA. But talked about pulsars, talked about neutral hydrogen, talked about imaging the galaxy, a lot of things that we do with the site, and try to give people an idea of what we're there for and all the things that we're learning. We gave a tour of the building, the dish, and the bunker, and Bill Thomas went in the bunker and did a demonstration of the amateur radio system in the bunker. While there, he made a contact on 20 meters with a nuclear ship that was in the Baltimore Harbor. Surprisingly, they were doing a special events station for Marconi Day, and they didn't even have a pileup on to this ship that was calling CQ, and he was like next door. It was so clear. And so Bill made that contact, told him what we were doing as a kind of a special event, and but not really a special radio event. And that was a lot of fun, and we demonstrated that. On leaving, as the kids started to leave the bunker after the tour, we encountered two very large rattlesnakes. I'm going to show you a couple pictures here. Let me go through the pictures of the event. Here's the kids and the adults in the classroom having lunch. There's the cafeteria, everybody waiting around for the next thing. And there's Roger taking pictures, and Roger and Bill and Paul at the console. This is Roger also took down the Eve package off of the mount, and so we've got that down now, and we'll probably do some work on that to fix the LNA that got broke. And this was the copper ground wire that we used to ground the dish. Anyway, while leaving the bunker, we encountered these two large rattlesnakes, and they kind of blocked the door, and they were there and rattling and such. So Rob went out and dispensed these two rattlesnakes, but they were pretty good size, and you can see they're probably about I don't know, maybe 3 feet long each, and had quite a few rattles. So they're not youngsters.
Is
The
this the inspiration for the Gadsden flag?
Yes, probably. Don't tread on me, right? So anyway, so we got rid of the rattlesnakes, and the kids were able to get out. I'm sure they'll remember that the rest of their lives. So we made an impression. But overall, this was a very good group. They had a lot of questions. It was a good exercise and outreach and educational event for the local community. And we made a little bit of money on it. And I don't know if we want to do this all the time, but for the locals, we got to do a few of these. So it was good. That's all I got. Oh, and there's the Eve package in the hub. So that's it.
Looks great. Thank you very much, Bill.
Yep.
Great report. Nice and sweet.
Yeah, try to get through these things.
You do a good job. All right. Well, thank you very much for everybody for visiting today. And we'll be doing this every month. We'll see how things go for next month. And we'll just keep on coming up with some interesting presentations. Sounds like we're going to have a lot of fun this summer with the dish. Hopefully we'll find maybe we'll find some new pulsars. Anyways, thanks for attending, and I'll send out a report on the group IO as what we discussed, and I'll send that out in a couple of minutes. So see you guys later.
Yeah, thank you.
Good night.
Good night.